A family wanted a member vaccinated with Pfizer-BioNTech. A mistake happened and the member received a mix-up of two unrelated vaccines, a first dose of Moderna and a dose of Johnson & Johnson. Another family member wondered if it were possible to make an estimate of the efficacy of two vaccines. A discussion ensued, centered around the person's knowledge of probability and statistics. According to this early chart, vaccine protection ranges from as high as 95 to 50%. These values are often revised and updated. Their accuracies are not important, as they are used only to illustrate ideas in the discussion. An analogy was used, that vaccine protection is like a leaky roof protection from rain. Like a vaccine efficacy, a roof has a rain block probability, such as 75% in this example. Can two vaccines, like two roofs, offer better protection than one? The leaky roof analogy is unlikely applicable to the science of immunology, but useful to describe the intuitive idea of improved chance. Can that be calculated? The strict answer is no. The only way to find out is to do experiments, or computationally simulate with an accurate physical model. However, the concept of probability can be used as a framework for analysis. Start with the get-through probability of the first roof. It is 1 minus P1, which is 0.25. Same for the second roof. It is 1 minus P2, which is 0.39. An assumption is needed. The two roofs are independent, and hence have zero correlation between them. Exactly what it means will be discussed more later. But here, this assumption means that the probability for rain leak through both roofs is simply a product of the two. Hence, it is 1 minus P1, times 1 minus P2. After some algebra, note that it is not simply 1 minus P1 plus P2, but has the term P1 times P2. The numerical value of this example is 0.0975. It means that the net probability for rain to leak through is reduced to 9.75%, better than either one alone. The probability of rain, not to leak through, is 1, minus, the leak-through probability above, which is P1 plus P2 minus P1 times P2. The net protection is not their sum, not P1 plus P2, but must be subtracted by product P1 times P2. Obviously, in this case, it would not make sense if one adds 0.75 protection of roof 1 to 0.61 of roof 2, which would be more than 1, which is obviously not correct. The final numerical value, the bottom line, is that using both roofs enhances rain protection up to 90%, better than either roof alone. If the previous naive calculation applied to COVID vaccines, the results would be too good to be true. All three vaccines together would give 99.9%. The problem is, the simplistic assumption that the vaccine effects were independent is mostly likely incorrect, and only experiments, that is, clinical trials can give the empirically valid answers. From a report in journal Nature July 1, 2021, it appears that multiple use of vaccines may help improve protection. Exactly how much improvement is still an ongoing research. Biological analysis of the vaccines is outside the scope of this presentation, which is about probability and statistical analysis. While the assumption of independent, zero correlation effect between the vaccines is unlikely to be correct, the point here is that the simple calculation is not useless. It provides a framework to analyze experimental results. If there are survey or clinical trial data as shown, for examples, for controlled groups, some without, some with just one type, and some with more than one vaccine, then this type of probability and statistical analysis is essential to determine the efficacy of vaccines and their combinations, which in turn, may provide insight to the fundamental biological mechanisms and suggest directions for further vaccine development. For example, consider this hypothetical data from 4 groups of large and nearly equal population. The unvaccinated control group has 365 cases of Delta variant COVID. Group with vaccine 1 has 91 cases, and so on. Then, simple statistics can be used to determine the vaccine efficacies as shown. Note that this is purely hypothetical and not real data. Efficacy of mixed vaccines, magenta color, at 83% is just purely hypothetical, for the sake of discussion. This is a quick illustration of how estimated efficacies vary as a function of simulated data. This one shows vaccine 1, which can be from 60 to 88%. This one shows vaccine 2, which can hypothetically be from 33 to 50%. A key concept is confidence interval. For example, this paper states that Pfizer-BioNTech 2 doses is 88% effective, with a confidence interval from 85.3 to 90.1. Confidence interval is needed, as estimated efficacy has uncertainty, illustrated by the spread probability density curve. This example shows the red dashed line marking the 90% confidence interval. 90% confidence means that there is a 90% chance that the true value of the efficacy to be within the interval. It is the range over which the integration of the bright shaded area is 0.9. The higher the population, the narrower the confidence interval, which means the estimate is more precise. Vice versa, if without sufficient sample population, small differences between various vaccines and their combinations may not be statistically meaningful. Based on published values, one can do reverse calculation, like reverse engineering, of the efficacy distribution. It is unnecessary to read too much into efficacies that are close to each other within a confidence interval. Back to the main question. All the vaccines aim to produce antibodies, with different methods, protein-based, viral vector, or mRNA, all to disarm SARS-2 virus. But can two or more different types of vaccines stimulate the body to provide better antibody defense than each individual vaccine? Whether the improvement is because of better learning by immune cells for antibody production, or more antibody variation that are more versatile to block the virus, or whatever, is a medical topic outside the scope of this discussion. Here, the topic is about applying probability and statistics concept to the question, like the use of leaky roof analogy, which is vastly simplistic compared to the highly complex immune system, but is appealing to the common sense of the lay people in this case. If there are real data of vaccine mixing, as indicated, the results can be put in a statistical perspective. If mixed vaccination is better than either one, that is, positive contribution, it suggests the vaccines contribute together. If it is higher than the baseline of P1 plus P2 minus P1 times P2, then the vaccines can be thought of as complementary. If it is less than the baseline, the vaccines can be thought of as overlapping in function and redundant. For the sake of completeness, there is no evidence, but theoretically, there is the possibility that the vaccines interfere and make it worse, which is negative contribution. Consider this combined vaccine baseline scenario. The analogy is two roofs with random and uncorrelated holes. The combined blocking probability is indeed approximately P1 plus P2 minus P1 times P2. In terms of probability, the vaccines can be thought of as each having its own independent complementary capability but with some overlap, hence subtraction from the total. If the two vaccines are highly complementary, the analogy shows two roofs that are perfectly complementary, no overlapped holes. In fact, the second roof is designed to patch every single hole of the first. Hence, the protection is additive, P1 plus P2, which, in this example, is 100%. Of course, real combined vaccine is unlikely to be perfect, but can be high, such as 98% or higher. In terms of probability, the two vaccines have minimal overlap. If the combined vaccine efficacy is not much higher than that of one vaccine, the other vaccine is redundant. The analogy is two roofs with holes that are completely overlapped, or maximally correlated. The second roof does nothing because its holes are lined up with the first, and anything leaks through the first also gets through the second. In terms of probability, antibody protection of one vaccine is just a subset of the more potent one, and hence, does not add significantly to the net efficacy. The concept of negative contribution, that is, efficacy is getting worse, is unlikely applicable, because all vaccines are designed to produce antibody with mechanisms that are unlikely to destructively interfere with each other. Although, never say never. As an example of negative contribution, each chemical on its own can make a person sick. But together, they reduce the probability of making a person sick. It appears vaccine cocktails might be needed for better protection, considering present and future variants. Statistical analysis of trial data will be important.